Three exciting talks. So the first one will be presented by Dr. Hemal Shah. He is a distinguished engineer and system software standards architect in the Data Center Solutions Group, or DCSG, division of Broadcom. He leads and manages a team of architects, and especially he is responsible for the definition of product architecture and software roadmap, architecture of all the product lines of Ethernet NICs, and he also leads the architecture definition of several generation of Nextstream E series and Nextstream products. And especially, they have been working on the Rocky adapters. And I indicated today morning, like we are working with them to have MPI support on the Broadcom. I showed some initial results. But this talk takes it to the next level, kind of saying like, how do you design better MPI libraries, and how do you do some co-designing with the adapter? Like what features they need to provide, what features we need to do. So this will be like a more like a researchy outlook talk, okay? So with that, let's give a hearty welcome to Hemal.
Okay, thank you everyone. Thank you DK for introducing me. I want to give a little bit history of my engagement with group here. It goes back quite a long, if you recall, DK. We started something like what is OMB now. With VI architecture, there was something called VIBE, VI benchmarks, which has some of the roots of what you see with OSU benchmarks today. So that was in 1998. That time I was at Intel. Then I moved to Broadcom in 2005, and our collaboration continued. Recently, we have been engaged with our Rocky adapters, and then we are working very closely with MPI group to see the tuning for Ethernet-based solution. And then we have virtual interface architecture, which was before InfiniBand. InfiniBand has roots of VI architecture. So that's, don't ask for my age, but that was the first thing I worked on from RDMA, and then InfiniBand, iWarp, Rocky. There are several generations. So as DK said, what I want to do today in this talk is kind of propose some ideas for where things are right now, where they're going, and what I think as a community we can work on at the MPI layer to really see the benefits of as we get into like 400 gig, 800 gig, 1.6 terabits, right? There are things that needs to work from top to bottom, not just improving network infrastructure, right? So all the way we want to go to application library level for the enhancement. So in this one, I'm gonna focus mainly on the small message latency and rate, but other things can also apply to other in general message processing. So that's what I'll try to introduce you to this number of researchy kind of ideas, right? Most of them are not there today in MPI libraries, but this will trigger some thoughts, and there may be more ideas beyond this. So with that, let me first just quickly introduce the problem, and then I'll talk about different ideas. So small messages, you ask, different people have different characterization. I put my here, everything below 1 KB you can call small, medium size, 1 KB to 100 KB, large. Why it's important for this talk, I want to focus on small messages. Depends on application. Maybe machine learning where the data transfer is very large, it may not matter as much, but there are other aspects of those applications. Plus there are a lot of HPC applications where you have either synchronization, control traffic, you're doing collectives on very small amount of data, right? So these generates a lot of small messages. Not only it does, it also requires very high message rate in some of the cases, as we talked, listen to that FFT talk where we were talking about ranks going into very high and requiring very high small message rate. So it is important that we look at the whole small message, how they get processed from top to bottom, and then really look into it, what can be done at different layers to improve the performance of small messages. So that's what I'm going to focus on. First, let's look at this. I kind of put in this stack as you start from all the way your fabric, and then you go all the way up to the application. So there are two nodes shown here. So what is happening at different layers? Ethernet fabric, as it scales 200 gig, 400 gig, 800, as you know, IEEE standards and the companies that are working on it, most of the switches have high radix, still multi-stage switch when you use. As switch hardware and software is improving, we are talking about few hundreds of nanoseconds of fabric latency, even if you build really your 10K kind of cluster. There is also a lot of active work going on in terms of reducing even the cable latencies, right? Whether optical, DAC. So those are, we are again talking about hundreds of nanosecond. PCIe going from Gen 4, Gen 5, Gen 6 implementation, with Gen 6 being flit mode, cut through, you are seeing lower latency on PCIe. And you look at all this implementations of in the NIC is primarily as you go to high speed state machine base, they're really very low latency pipelines processing all the ROCE. Entire transport is offloaded. All the QoS policies are already offloaded in the hardware. And then from user level, you have direct access to the hardware. So my point, that there's a lot of work already happening at those layers to reduce the latency. Now let's go to the first layer in the software, verbs layer. API has been defined for quite some time. It's been out there. But as you start seeing the interaction of verbs layer with the hardware as well as the upper layer, there are things you can do in the library to really optimize your software data path, because after that is everything is hardware data path. But then what about your software data path? That adds to your latency. And then as you move up to the MPI layer, whether this is MPI, UCX, at some point it's interacting at the verbs layer. So let's look at that messaging layer, how it handles the communication with application above, and then how it interfaces with the verbs library will make a big difference. For example, let's say I have optimized end-to-end latency, which are sub 1 microsecond at the verbs layer today. Then if MPI layer adds 1 microsecond overhead, now I'm talking about doubling the latency. Similarly, let's say the hardware is capable of sustaining 200 million messages per second. Do you have a system where the library processing, it does not take that much CPU cycles? So as you scale the number of CPU cores, one CPU core today is not even sufficient to get to few million messages per second. So anyway, people are using multiple cores. What I'm saying is, even with multiple cores, your library overhead, will it be able to get to the underlying message rate that infrastructure is capable of? And those are the questions I want to raise and then talk about some of the ideas, right? So for the rest of the talk, I'm just going to focus on the MPI layer and really share with you guys some ideas. So these are some of the matrix, as I said. CPU, it's very simple. How many cycles you spend per message is going to impact your latency of software data path. Also, it's going to impact your message rate, because depending on number of CPU cores, you will decide how many cores I have, and then that overhead times number of cores, that's going to be your CPU sustained message rate, right? So it's important to take those two matrix into consideration when we start talking about this. Okay, so let's start with this. This is where there are copies. Copies have always been an issue. If you go to the TCP IP stack, there are multiple copies. But even with MPI, small messages, there are copies involved. Why? Because when an application posts an MPI send, with the semantics of MPI, you may copy that data into some internal buffer and return that send is done. But that packet has not yet gone on the wire. So then what happens? So that's first copy. Then after that, that MPI library is talking to verbs library and then posting this as a work. If it is a small message, it may send this as inline data. So then what happens is that inline data gets copied into a Wookie. So that is your second copy. And then if you really want to get to the low latency, you are, instead of trying to use the DMA model to get the Wookie, you may want to push that using MMIO directly to the NIC buffers. So there is MMIO cost. So if you really see this, and this is the send side, on receive side, you can think about when packets come in, there's going to be first in the posted receive buffer, it will get DMA data, and then from there, it will get copied to the user or application buffer. So some of these copies you can think about. If you do the co-design, you can avoid. Some may not be avoidable. So there are two different ways we want to look at it. First, at least we should start thinking about what kind of optimization you can do for the copy operation. And I'm bringing some of the experience that from the DPDK world that we have for our devices, where use of vector mode really helps with reducing the cost of CPU cycles that you spend per message. Today's MPI library, I do not know whether they really take advantage of things like AVX512 and other. Whenever there are copies involved, then vector mode processing really helps with that. And then most of the CPUs today, they already have very advanced set of instructions. So by using that, even with the copy, you can improve the latency and message rate. Other thing is you are seeing all this NUMA architecture where your buffers are matters a lot, because now whether you are within a cluster, you're within a NUMA, or you're doing copies across NUMA, big difference in terms of the overhead. So you want to bring some locality to yours. So if your process that is running, if you have all these intermediate buffers which are pinned and locked to that cache on which your process is running, that'll really help with the copying operation. So these are some simple ideas that libraries can incorporate to reduce the cost of copy. So that's one area. Other one interesting here is most of the MPI libraries have this message coalescing mechanism. So what this is, as I said, when you get application message, it's not directly sent on the wire. If these are small messages, they are locally copied inside. Depending on what kind of coalescing logic you have, you will have up to some n number of messages being collected, or after some time, you will start posting those. So when you do that, what you're doing is you're trying to amortize your cost of sending a packet which may include more than one message. So you can coalesce that. This may improve your message rate, but it comes at the cost of complexity in the MPI library. Plus, it may impact your latency. So for really latency sensitive application, coalescing is not really that beneficial, but it does help with the message rate. Other thing here is at the verbs or lower layer library level, you do have these APIs where if the upper layer like MPI layer has multiple messages to send, it can just post that in a single call as a list. What's the benefit of using that kind of call is instead of having, and you might argue like, okay, it's a user mode call. No, it's not just the user mode call. When you do this kind of list processing in a single call, what it helps is underneath library, they know that you are sending this many messages on this queue pair. So it can do some kind of doorbell moderation. What I mean by that is it can post all of those and then maybe ring doorbell once per list. So now you have reduced the cost of MMIO, which helps with your processing. And then that will also improve your message rate, because anyway, you are sending this in a list. So it's going to go out as one by one. And then that, because you had all these multiple messages being queued at the same time and they are being processed more efficiently, your message rate will be better. This may adversely impact your message latency. So every time I see coalescing, I run into this. Most of the time you have some kind of control variable which says you enable coalescing or not. So it's all or nothing. It doesn't work for all type of traffic. So how do you come up with some kind of sweet spot where you do not impact the latency of the messages, still allow coalescing for the messages you want to do? That's what I will call selective bypass of coalescing. So you can have coalescing logic inside your MPI library. There are a few examples I can give here. So for example, if you get MPI send receive and a very small message, generally these are meant to be low latency kind of neighbor kind of communication. So you can bypass your coalescing for that and right away post those messages. That's one example. Another one is you can have different class of services supported by MPI library. I'll talk about that later also. Then if you have message come with a class of service which is for low latency, you'll use that as a hint to not coalesce. For everything else, you will coalesce. So this type of coalescing, more selective or dynamically making the decision to coalesce messages or not, really helps with the MPI library implementation. And what this will do is it will give you best of both worlds. You'll get low latency as well as high message rate. So this is another area where MPI libraries can really help with the small message performance. Third one, this may sound pretty obvious, but not necessarily it's true today that all the MPI buffer management is fully optimized for different architecture. But what I mean by that is you want to avoid any kind of intermediate copies. We don't have a model today in MPI to transfer the ownership of buffers between different library. So this is something to think about if you want to avoid the copy where the buffers for one library can be exposed to the library below it, then it doesn't have to make the copies. Or like, for example, on a receive buffer, if you have a common receive buffer pool, which is provided by the upper layer library, but then packets are received in that and those buffers are passed back to the library. So now you avoided the copy for that between the libraries. So these are some of the ideas that at MPI library level you can use to do a better buffer management. Caching is another example, like having a buffer pool per core cache, and that's pinned down. That really helps with the locality. Moving to another area where, so today, I believe libfabric has some of this, but what I'm going to talk about is giving some type of hints between the library really helps the overall co-design. What I mean by this is MPI library posting a work request to the library below it, let's say verbs here. If it knows already it's going to queue up more, it's better for it to let the library below it know about that. I'm queuing this up, more things are coming in the pipeline. What that enables is the library below can now optimize saying, oh, if I'm doing some kind of moderation of ringing the doorbell, letting the NIC know about the work, I know there is more work coming on this QP. Maybe I do some kind of coalescing myself. And then this way you amortize the cost. That's one. Other one is the library itself can give hint on per queue pair or per work request base saying, this is more like a low latency request, or this QP is going to be used for low latency traffic only or high message rate traffic only. Based on that, with that kind of attribute, if the library knows, it can do different processing for different queue pairs. So that's the second way the hint will be useful for the overall software. And then third thing, this is not commonly used. Generally, verbs has this protection domain, all resources are within that, and then you try to, within the verbs library, you have to maintain locks because it's not guaranteed to be thread safe. But there is this thread domain verbs which MPI library can use, and that gives hint to the verbs library saying, if there are resources which reside in the same thread domain, then I don't need to have extra lock on this. So this way you can avoid those kind of intermediate locks in the library. Otherwise you will see like multiple locks are being taken at different layers in the software. So that, and again, those with more processes, more shared data structure, those locks do not scale well. So by avoiding it, you really benefit. So this is an area to think about. Some kind of hinting between the different software layers can optimize the software data path. And last, what I want to say is most of the NICs you see today, they are already supporting multiple class of services per port. And what I mean by that, these are different cost queue. It will do the classification in the hardware. You can have all different types of strict priority, weighted fair queue kind of policy applied to those traffic classes. You can have bandwidth share between them. Those are already available in the hardware. What happens at the MPI layer? From the layer above, when you look from Rocky side, everything is looking like Rocky traffic, right? Here we have an opportunity at the MPI layer that if at MPI layer you can differentiate traffic by saying, okay, this is more latency sensitive, high priority, maybe I'm going to put this into a different class of service queue than more throughput oriented. Collectives may go into different ones, so I can avoid interference of that with other kind of send receive operation. So these are some examples, but the idea is if you use separate class of service queues, which are already supported by the hardware, and then there's already plumbing that's available verbs and below. If the upper layer library MPI and verbs library can take advantage of that, now you can do this when you create a queue pair from the MPI library. You can say, I'm going to create this for low latency. So put that in the separate cost queue. Or you can have some kind of, you create a cost queue profile at the beginning from MPI library saying these, I want to use 3 or 4 class of service. Based on that, underneath the hardware and the QoS, hardware will get programmed. Once that happens during initialization. After that, you can start using that on per queue pair basis. And that way you can have this kind of separation of traffic. Each one gets different kind of QoS all the way from the software below to the hardware. And of course, the network infrastructure already supports this kind of QoS policy today. So that's also another area where I think there is room for innovation from MPI library standpoint. And I'm using general MPI library. I know this is MVAPIsh2 group, so MVAPIsh2 is a good start, but there is nothing specific in here for MVAPIsh2. Any MPI library or upper layer library should be able to take advantage of this kind of ideas. So I think with that, it's a very simple set of ideas, but that may really help as we scale to really large node counts and the speeds we have talked about, because now we will be counting nanoseconds in the software. And this is where all this comes into picture. So I think that's mainly, I talked about different ideas here, but there may be other ideas. What my call to action to this community is, let's start creating this kind of co-design now. We are at a point where the different layers have already matured. Now it's time to like really look into the total solution and what other software optimization can be done. So with that, let me take a pause. Any questions?
Any questions from here or online?
Could some of these enhancements be done outside of an MPI library by having a tool load the MPI calls and then look at the messages and then say bunch them together and then transmit them in some manner? Could some of these operations be independent of an MPI library?
So really good question. Just to can some of this optimization be done independent of MPI library? Short answer is yes. MPI library can come up with its own profile, but let's say you have a profiling tool which figures out for this application, if I separate traffic in this and maybe provide that kind of provisioning before the MPI application runs to the layer below, that's one way. Other ways, it can be maybe done transparently below MPI library by the verbs library. The harder part there is now you're making some guesses, right? That this traffic is meant to be given this class of service. Versus if MPI library is directly doing it, it knows for sure that this is how I'm gonna separate out the traffic. But I think it's possible.
Thank you.
I believe what Samir is saying, like a tool like Tau, they have a lot of understanding of how the code is running. So he's saying, can it be taken at a higher level, saying, let's say the application is sending a lot of these messages back to back. It detects a pattern. If I understand, then tell the lower layers through a control variable or something to the MPI library, saying, okay, coalesce this. All right. So
yeah,
I think it can
be done. And in fact, for that kind of selection, we can have very simple way of describing specific policy. And then it just gets executed layers below it. You can just specify that policy.
Thank you for nice talk. I just want to make sure that I understand correctly. You suggested to coalescing messages and batching the requests to reduce the overhead. I think that those kind of mechanisms can reduce the overall overhead and increase the bandwidth. But latency-wise, it can be worsened. So what do you think about that?
Yeah, good question. I think maybe I went over very quickly. Batching, if you do all or nothing, I absolutely agree with you that it impacts the latency. That's why you need to have more like selective batching when you know the traffic is more or less throughput oriented or message rate oriented. But for low latency, you bypass that logic and don't batch. I think that's where the library can be very intelligent about that.
how do we know whether we are going to equalizing the interrupt, or how many interrupts should be equalized for the better performance? Well, we just, as a hardware guy, we just provide the hooks. It's basically the setup of registers to the application software, and then, well, software, so that layer of software needs to understand its own application to utilize those hints. And until it really runs the application and find the result coming back from the underlying architecture, it may not know.
It may not. Yes.
So I would like to learn more thought of yours.
No, really good question. And outside of this, the coalescing, what you talked about on the standard non-rocky traffic, those are the things we face. So I'll say three things. One is you got to have very good default. And it's very hard to come up with those kind of good default. That's one. Second is, at least if you can categorize things into profiles, where you can say, I'm running HPC application, I'm running message or machine learning application. Based on that profile, everything below it is kind of selected in a way saying this is latency sensitive, optimized for latency, this may be throughput oriented, this may be more balanced. Those kind of things, you can come up with few, not too many profiles, and then maybe allow application developer to select one when they run the application. At least you minimize not setting like too many parameters. The third thing that I can say is it'll be really good if MPI APIs can be extended for applications to provide hints saying, okay, I'm creating this set of communication endpoints, and what is my performance profile for them? And performance profile I'm using very loosely, but performance profile could be balance, low latency, high bandwidth, right? Something like that. I think those are the things, and some kind of profiling and automation will definitely help, because end of the day, application developers, they do not want to specify too many knobs, and that's where things fall apart, right? You give too many knobs, but the users, they don't understand. They say, what's the default? Just go with that. So there is definitely some work needed to make it more user-friendly for application. So that's why, yes, we need to go to library, but a library needs to be smart enough in a way that you don't require too much configuration from application. Absolutely. Agree.
So I think just to remain on the schedule, I think we can let's give again thanks to Hemal.
Okay, thank you.
Oh, sorry, there is a question. Yeah, the day tour people, please follow me.
So,
Until I finish, you have to wait. Just wait.
all right, sorry. Hopefully this will be quick, but Adam Moody has asked, comment on coalescing. I wish there was a way to issue a list of MPI ISENDs from the application level. When the MPI library sees an MPI ISEND, it often fires the message to the network immediately. But many times an application has multiple sends to be issued at once, and it would be useful to inform the MPI library about the whole set rather than one at a time. One can get close with MPI start all or neighborhood collectives if the pattern is fixed, but it sometimes feels like there's a gap to me.
Yes, really good question. So I have seen code where literally application is doing n number of MPI sends, but one at a time, right? So there are two things that you can have more optimized API where a set of messages can be posted at the MPI layer in one shot. That's one. Other one is, as I was talking about hint, the application can post a message and say more is coming. That way you can coalesce at the MPI layer. Those type of enhancements, both at API layer and library level, will be really useful.
So thanks again, and then we'll move to the next talk, and Ben will follow you. So.